Hi everyone, this is a short lecture on z-scores. Even though there will be some discussion of formulas and calculating things in this lecture, really the important thing is to understand what a z-score is conceptually and what it can be used for. And then how it relates to sort of the normal distribution, all of which we're going to discuss here in this this short video. So what's a z-score? It's really a way of converting raw scores to a different to sort of a different metric so that we can compare apples and oranges. To calculate a z-score, what we need is the raw score. We need the mean of all the scores in the sample. So we need the raw score from an individual score. We need the mean from all of the scores in the sample, and then we need the standard deviation and all of the scores in the sample. So let me give you an example here real quick. Here's a sort of overly simplistic example that has to do with test scores. So student number 1 is happy because she got a 60 on an exam in her research class. On the other hand, student number 2 is sad because she also got a 60 on an exam in her research class. Same score, different reactions. Why would that be? Let's ask, right? So what it has to do with is what is the score, right? What's the mean score relative to that other person's score? So both of these graphs here show normal distributions, right? Mean, median, mode, all occurring at sort of the highest point in the graph, and very few scores occurring at either of the tails. So student 1 is happy because the mean score in her section was a 50, so she was 10 points higher than what the mean was. On the other hand, student number 2 was happy, or I'm sorry, student number 2 was sad. Again, we see the same normal distribution, and that's because her score was 10 points lower than the mean, which was a 70. So if you've ever been in a class where an instructor curved grades, essentially what they're doing is they're setting grades so that they exist on a sort of normal curve or a normal distribution, and then students' scores align with where they occur on the distribution of normal scores. Okay, so let's talk about this a little bit more. So z-scores are really a way to talk about where a score falls in a distribution. To calculate the z-score, we take the raw score, we subtract from it the mean, and then we divide that by the standard deviation. The z-score really is the number of, let me move my picture here real quick so we can see this last bullet point. The z-score really is the number of standard deviations a score is away from the mean. So it's really a way of calculating the distance any given score is away from the mean. So a z-score that's very small would mean that it occurs very close to the mean. A z-score that is very large means that it occurs very far away from the mean. Same thing if we were to look at positive and negative. So a z-score that is positive means that it occurs above the mean. A z-score that is negative means that it occurs below the mean. So ideally, if we were talking about z-scores relative to a test, it would probably be desirable for a student to have a score that was positive, because that means that they were a z-score that was positive, because that means that they're above the mean, and then a z-score that is also very large, because that means they're far above the mean. So here's sort of this same example. Why don't I leave myself there? Okay. So here's student number 1, and if you remember, student number 1 got a 60 on the exam, and she was happy about it, right? So we know that her score occurs above the mean, right? Because the mean was was 50. So if we were going to calculate this student's z-score, we would get to 1. I'll tell you how we get there in a second. But we have the average score in class, we have the standard deviation of all scores in class, and we have student number one's score in class as well. So we would take the score, we would subtract from it the mean, right? So 60 minus 50 is 10, and then 10 divided by 10 equals 1. So student one's z-score on her exam is a 1, right? That means she is positive, so she's above the mean, and she's some distance from it, so that means she's actually quite far above the mean. So a 1 in a z-score on this exam would actually be very good. Student number 2, on the other hand, is sad about her score, even though it's a 60. So again, if we take the mean is 70 this time, same standard deviation of 10, and her score, same score of 60. We take 60, we subtract 70 from it, we get minus 10, and then we divide that by 10. Now we get a z-score of -1, right? So what does the negative tell us? That means it falls below the mean, and the 1 gives us an idea of how far away from the mean it is. So if for some reason we had calculated, student number 2's score, and her z-score was -0.5, that would actually be a better score than a -1, because it would be closer to the mean, right? Still negative, so still below the mean, but a little bit closer to the mean. So that would actually be a higher score. If we wanted to use an example of another student from section 1, right? In section 1, the mean score was 50. If this student got an 84, we can call this person, student 3 or something like that. We could go through that same calculation. The student's score minus the mean divided by the standard deviation, which would give us a 3.4. So again, it's a positive score, so that tells it's above the mean. And this tells us that it's quite a bit of a ways above the mean. So this is actually a very, very good score relative to the mean and the rest of the scores. Well, we'll get to why we use z-scores here in a second. An example that's a little bit more germane. But let me just reiterate a couple of things real quick. Z-scores can be positive or negative. A positive score is above the mean, negative obviously below the mean, and the z-score is simply the distance away from the mean. The nice thing about z-scores is that the mean is always 0. And that's what makes numbers that fall above the mean positive, and z-scores that are negative sort of fall below the mean. Z-scores can also be turned into percentages, which is sometimes useful. So this is sort of let me do this way. Here's our normal curve again. This time, instead of using raw scores to have created this normal curve, we're using z-scores. So in this case, the mean, the median, and the mode are still at the highest point in the z-score, except that this time, because we've standardized these scores, right? We've converted them to a different scale. The mean actually now is 0. And what this means is that 50% of the scores would occur above the mean, 50% of the scores would occur below the mean, right? And so in this way, one of the ways to think about this is, since the mean, the median, and the mode are also, are all the same line, this also means that this line is where the median is. And so just as if we remember our sort of rules about the median, the median is the place where 50% of scores are higher and 50% of scores are lower. A bit of review about the normal curve real quick. 68% of scores are within 1 standard deviation above and below the mean, right? 34% of them will be above the mean, 34% of them will be below the mean. One of the places you often encounter z-scores is in standardized testing, and so if you remember back to taking something like the SAT or the ACT or something like that, or really any standardized test, including social work licensing, exam, if you score in, typically what they give you is a percentile ranking. So if a student, for example, scored at the 84th percentile, that means that 84 and change percent of students would have scored below whatever that student's score was. The difference between 84% and 100% would be the number of students who scored above that student, right? So in this case, it would be just below 16% of scores that would occur above student one's score. So that's typically, when we see standardized testing, the higher the percentile ranking, typically the better. So the higher a percentile ranking means the sort of further away from the mean a person is, the larger their z-score is, and the fewer students that have sort of scored above them. So obviously scoring in the 90th percentile or the 95th percentile or the 99th percentile would be sort of a marker of a really good score. Suffice to say, this sort of sidesteps all of the social justice issues that have to do with standardized testing. Again, this is really just an example, and I bring that up because it's a place where most of us have encountered z-scores before. One of the other ways, or one of the examples we might think about as social workers that's a much more sort of consistent with the kinds of things we think about would be something to do with poverty, or something to do with maybe a score on a measure of mental health problems or something like that, or mental health functioning or social functioning or something like that. And typically when we're concerned about poverty, we're thinking about people who are falling below the mean in terms of income. And so typically their z-scores are negative and very small, because they are so far down on sort of that socioeconomic status. If we were to go back to that, those same testing examples kind of before, since student 3's score was so good, if their z-score was 3, they would have scored in the 99th, the 99.9 percentile, which would obviously be excellent. Very few people would have scored above that person. Same thing with student number 2, since their z-score was -1, right? They would have scored in about the 16th percentile. That means about 16% of students would have scored lower than them, while 84% of students would have scored higher than this particular person. And again, this is test scores, and I think the poverty example is something that's much more, I think, relevant to social work. But again, this was just sort of for purposes of illustration. So just a couple of things to reiterate about z-scores real quick. They're really sort of a ruler. They place data on some kind of standard scale. And if we wanted to compare, for example, scores on different measures of depression, sometimes people do this in what's called a meta-analysis, and they'll take all of the studies for example, they would take all of the studies that scored or that looked at depression as some dependent variable, and since there's different measures of depression, the PHQ-9, the Beck Depression Inventory, so on and so forth, we need a way to sort of combine those scores. And so the way we would do it is to convert them all to z-scores. And that would let us aggregate data from across studies into the same study. And that's sort of the purpose of a meta-analysis. So it's like a ruler, it places data on the same sort of standard score. And that the z-score then literally is the distance of a single score, the distance away from the mean in some standard deviation units. We can convert it to percentages if we want, like we talked about. And the useful thing about this is to sort of identify a cutoff, right? So this, if we were thinking about, say, depression or some other mental health problem, and we aggregated data from a bunch of different studies looking at percentages, right, assuming they're sort of normally distributed, would help us identify people who are really depressed, or really, really, really depressed, or not at all depressed, right? So it would help us identify people who were sort of in need of help. And similar things, I picked depression just as a sort of, common mental health problem, but we could do the same thing with PTSD. We've done the same thing with alcohol abuse. We've done the same thing with all of the other sort of problems a social worker uses. So they are sort of useful things. So as always, any questions, feel free to let me know. Thanks for watching.